Hi, Mr. DeLiegro here. I want to go over the structural properties that we're going to be looking at in the next few days. So, first of all, we're going to be learning about moment of inertia, which is the cross section measured in inches to the fourth that gives information about the cross sectional area distributed about a centroidal axis. Now, we went through and learned about centroids. Now we're going to get more in depth. The stiffness of an object related to its shape. In general, a higher moment of inertia produces a greater resistance to deformation, which means bending or stretching or any other type of deformation or breaking. So if we look here, we have two beams. We have a beam A that is placed as a joist, and we have beam B, which is placed as a plank or flat. They are the same material. They are both Douglas fir wood. They are both 8 feet in length. However, if you look at the width of the plank, it's 5.5 inches, where the height of the of number A of the joist is 1.5 inches, and their height is reversed. Okay, and they have the same area. Okay, so what distinguishes beam A from beam B? Let's take a look. Will beam A or beam B have a greater resistance to bending, resulting in the least amount of deformation if an identical load is applied to both beams at the same location? So what we're going to look at, we have a load, same location for A and B, but what we want to see is its resistance to that load. And you can see that beam B, right, has greater deformation, right? There's very slight movement in beam A, but plank B, you see that load is bending, and we have deformation there. So why did beam B have greater deformation than beam A? Well, we look at the moment of inertia. The difference in moment of inertia due to the orientation of the beam. So we're going to be calculating it based on the rectangle. So the formula for moment of inertia is I is equal to base times height cubed divided by 12. Okay, so you're going to see that the moment of inertia is greater in the beam because the height was greater. As you can see right here, right? So for beam A, we have 21 inches to the fourth moment of inertia, where with beam B, it's 1.5 moment of inertia. So you could see that is a huge difference. And there you go. You see 21 inches to the fourth versus 1.5 inches to the fourth for beam B. It's 14 times stiffer, actually. And the reason why we use these composite beams is we can do more with less. As you can see, so we have just a rectangular shape, two rectangular shaped beams and an I-beam. You can see that the area for these beams is labeled right there, although beam 3 is 23.8 inches squared. But when we look at this beam, the I-beam, even though the moment of inertia is a little less than beam 3, it still is more efficient based on the fact that we're using less wood. Okay. Now we get into the modulus of elasticity. That's the ratio of the increment of some specified form of stress. It defines the stiffness of an object related to its material chemical properties. Okay, so moment of inertia was how it was orientated. This one is about its chemical makeup. In general, a higher modulus of elasticity produces a greater resistance to deformation. So here we have beam B, which is ABS plastic. It's 8 foot. They're the exact same orientation and the same moment of inertia. But what distinguishes beam A from beam B? Well, will beam A or B have a greater resistance to bending, resulting in the least amount of deformation? Well, let's take a look. So we see that beam B actually has more deformation. So when the load is applied at the same point. So what does that tell us? It tells us about the chemical makeup of the plastic beam, right, is less than the difference of that of the wood. So it's the difference in material modulus of elasticity. So in order to find the characteristics of objects that affect deflection, we are going to use delta max. That's the maximum change, the applied force or load, length of span between the supports, and modulus of elasticity and moment of inertia. So here we have, you could see that the modulus of elasticity is so much greater in the Douglas fir than the ABS plastic. And then here's our formula. It's delta max is equal to the force times the length cubed divided by 48 times the moment of inertia times the modulus of elasticity times the moment of inertia. You're going to get formulas here, or you're going to get problems where you're going to have to do some formula manipulation where you'll have everything but the force or the modulus of elasticity, and you'll have to solve for that. So calculate beam deflection for beam A. So there we see we have 250 pound-foot force over 96 inches cubed. And make sure that you are always in the correct unit, which is inches, okay? So not 12 feet, not whatever. So, and then we have divided by 48, which is a constant, times the modulus of elasticity, times the moment of inertia. And we come up with a delta max of 0.12. And then when we do the same for beam B, we find that delta max is 0.53. So there we have more deformation, quite a bit more, as you can see. All right, quite a bit more deformation. And that's it. Take these notes and do the assignment. Thank you.